Alright guys, so let's get into some more inequalities here. This one, a rational inequality, but a little different because this one actually has two terms that are being separated by the addition sign in the middle. So in order for us to set up and be able to use that sign chart to determine the positive and negative intervals here, we're going to need to combine these and get them into one fraction. Okay, so what we're going to do, we're going to actually take a look at these denominators here, and we're going to try to just combine these with a single common denominator. So in this case, we're just going to have to use x plus 3 and x minus 1 as a common denominator now for the two terms. So I'm going to rewrite the problem, okay, much like adding, simple fractions. You got to get that common denominator. And for this case, if I'm looking at the term on the left here, it just had the x plus 3, so I would need to multiply top and bottom by x minus 1. Okay, so the numerator is going to become 5 times x minus 1. And the other term, we're going to need to multiply top and bottom by the x plus 3 so that it will have each of those terms in the denominator as well. Okay, now here's the one point where sometimes you can get yourself going in circles is in the previous section, or when we were solving equations, we were kind of canceling things out. Now, no, we have a different goal here. First off, the x plus 3 did not cancel out in that case, and we don't really want it to. Okay, we're not doing this to simplify things. We're doing it so that we can have a common denominator. So you don't want to cancel those out in this case. What we wanted in this case was to get fractions with the same denominator so that we can then combine them into a single fraction with that same common denominator. Okay, and there's still a greater than 0 over here. Here's where now what I want to do is actually multiply out up here so that we can start combining any terms we have in the numerator. Okay, so I'm going to distribute each of these out. Notice I didn't cancel anything out yet. So if I had canceled them out, I wouldn't have anything to multiply. Okay, now we do that with equations when we're trying to get rid of the denominators. Okay, and this is not what we're doing here. We are actually combining two fractions into one. Okay, which is going to allow us to finish the inequality. Okay, so in this case, if we start simplifying that numerator, 5x plus 3x, we have 8x. The negative 5 plus 9 is a plus 4. And the common denominator was x plus 3 times x minus 1. All right, so this is basically what our problem boils down to. Now that we've simplified it into a single fraction, we can now start setting up the critical values and doing a little interval test on these. Okay, so critical values, again, are always going to come from if there are any restricted values and also any values that would solve the equation. So critical values for this one, we have two restricted values because of the denominator. X equals negative 3. Okay, well, the expression becomes undefined. If x equals 1, the expression would become undefined, again, because the denominator would be 0. Okay, but one other thing we could do, because remember, critical values, again, are not just the excluded values, but also anything that would actually solve this as an equation, meaning which x would make it equal 0. So since this numerator is factorable, that's going to help us visualize what's going to make the fraction 0. If we factored a 4 out of there, it would be 2x plus 1. Okay, and the denominator is still x plus 3x minus 1 greater than 0. And that lets us see that if that 2x plus 1 were set equal to 0, okay, that would make the whole expression equal 0. So 2x plus 1 equals 0 would give us another critical value of x equals negative 1/2. Okay, and again, that would make the expression actually equal 0. Okay, because again, if in a fraction, right, if the numerator is 0, right, if this guy is 0, that's going to make the whole expression equal 0. Okay, so we have three critical values. We're going to get those put onto the number line, and we're going to do a little interval test and do a sign chart and see what we get. Alright, so let's get our little sign chart and interval test ready to go here. So I'm going to plot my number line. Right, let's do a nice number line here. We're going to need three critical values on there. The lowest one is negative 3. Then we had negative 1/2. And then we had positive 1. Okay, and what I'm going to do when I go to do my test, my sign chart test, I'm going to plug them into this version here, which is the factored version. And then I'm just going to ask myself again as we go, are each of these factors negative or positive? and then does that satisfy the original inequality that we're talking about up here, okay? Or maybe not the original, but the simplified version. So if we go to test something less than -3, for example, let's test x equals -4, and let's see what happens. Okay, if I'm plugging that in up here, right? So the expression is 4 times, and then 2x plus 1. So if x is -4, that would be 2 times -4 would be -8 plus 1 is still a negative number. Okay, in the denominator, x plus 3 would still be negative, and x minus 1 would still be negative. Okay, so that means we have a negative up top. The bottom is negative times negative, which is positive. Okay, and a negative over a positive is negative. So in this case, is that greater than 0? And the answer is no. That interval does not work. Okay, the end point, -3 itself, also does not work because that, remember, caused the expression to be undefined. Okay, let's test something in the second interval. If we wanted to test a number between -3 and -1/2, like let's test, for example, -1, for example. We test x equals -1. Okay, and I'm going to throw it into the same factored expression. There's a 4, 2x times 2x plus 1. If x is -1, that would be -2 plus 1, which is negative. The denominator, x plus 3, that factor would be positive. And the factor of x minus 1, if x is -1, that would be negative. So in this case, we have a negative numerator, we have a positive times negative, we have a negative denominator. So as a whole, the whole expression would be positive. It would be greater than 0. Okay, so that works. That interval is going to work for us. All these numbers work, but when we get to -1/2 itself, that actually makes the expression equal 0. And in this problem, we have to be greater than 0, so that needs to be an open circle there as well. Okay, so we have these numbers in between, but the endpoints are open circles. Okay, let's see what else we got. If we want to test something between -1/2 and +1, why don't we test 0? Okay, it's one of my favorite numbers to check. Right? Let's test x equals 0. All right, so going into that factored version, we have 4 times 2x plus 1. If x were 0, that would be positive. The x plus 3 factor is positive. The x minus 1 factor is negative. Okay, so that gives me a positive up top, a negative on the bottom. So as a whole, positive divided by negative is negative. That's not what we want here, so this interval does not work. Okay, let's make that small. And finally, what about numbers greater than 1? What if we want to test 2? Let's test x equals 2. All right, so if we test x equals 2, it's 4 times, so 2x plus 1. Okay, if x were 2, that'd be 2 times 2 plus 1, that would be positive. The x plus 3 would be positive, and the x minus 1 would be positive. So that's giving us a positive over a positive, which of course is positive, so that works. Okay, but the endpoint of 1 itself did not work because that was an undefined value, but we just showed any number bigger than 1 is going to work. Okay, so our final solutions, if we want to write these as intervals, we would be from -3 to -1/2 using parentheses, right, because neither endpoint works, or from 1 to infinity. All right, and just graphically, here's just kind of a graph of the function. I graphed the original. Let me see right here, and as you can see, we wanted to know when this thing was greater than 0 originally, and we said that it was between. Let me see if I can highlight on top of this. This is just kind of a way to check things out. In between when x was -3, I'm sorry. So all of this stuff right here to -1/2, the y values are above 0. And then also all the y values are above 0 when x is going from 1 to infinity. Okay, so we can see our critical values again just on this graph. We're at -3 here. That's where it was undefined. We have that vertical asymptote. -1/2 right here is where the expression equaled 0. and then we had the other vertical asymptote at +1. Okay, and we see the intervals that we highlighted. Let's try and do the same color. This one's going to match up from -3 to -0.5, and then from 1 to infinity is shown right here. Okay, so again, hopefully that graph kind of helps visualize things, but again, we kind of solved the problem algebraically and did all the steps. All right. All right, let's take a look through. Let's walk through one more of these. So let's take a look here. We have x minus 3 times the square root of x plus 1 greater than or equal to 0. Okay, and we want to solve the inequality again using that spit method where we solve, then we plot, and then we do interval test. Okay, so with this one, we have some critical values here. Things that would make the expression actually equal 0. Since it has two factors, x equals 3 would make the expression equal to 0. And then also under the square root there, x equaling -1 would make the expression equal to 0. But also note, since there is a square root function here, that needs to be positive, right? So we know that x plus 1 has to be greater than or equal to 0 for this thing even to exist. So x has to be greater than or equal to -1. Otherwise, the expression is going to be undefined. Okay, because again, we would have a negative under that square root there. Okay, so just kind of keep that in mind as we do this. Now let's think about as we go to plot those, and then we'll do our sign chart. So we have -1 here, we have +3 here. Okay, we know that at -1, sometimes I like to just write what the value is up there, whether it's undefined or equaling 0. At these two x values, the whole expression equals 0. Now for this problem, that's okay because we have the equal sign there. Okay, this interval or this number line is going to help though for this one because remember we said that x has to be greater than or equal to -1, otherwise the expression is undefined. So we know if x is less than -1 out here, oops, all those x values that are less than -1 actually make the expression undefined, so we don't even need to worry about it. Okay, so let's just test. I don't even need to test anything less than -1. I mean, you could, but then hopefully as soon as you plugged in, you would figure out that that's going to be an imaginary number, and there's no way that that result is going to be greater than or equal to 0. But I'm just going to leave that whole interval as undefined. So let's just really test something in between -1 and 3. So let's test like x equals 0 and see if that interval works or not. So if we test x equals 0, and when we test in this case, we're just going to test it right into the original inequality and see if it's true or not. So if x equals 0, the x minus 3 factor would be negative. Okay, the square root of x plus 1, that would be positive. So is that greater than or equal to 0? A negative number times a positive number would be negative. So in this case, that interval does not work. Okay. Now let's just test. What if we tested a value that is greater than 3? Okay, let's test x equals 4. Okay, so x equals 4. Again, I'm going to plug into the original inequality. So the factor x minus 3 in that case would be positive. The square root of x plus 1, if x is 4, that would be positive. Is that greater than or equal to 0? Yes. Okay, so in this case, that interval works. Now 3 itself works, right? Because at 3, the thing equals 0. So that works. Any number there works. Now just be careful. Don't miss out. The -1, that endpoint right here makes the thing equal 0, right? So that actually is part of our solution as well. -1 worked. Okay, so our final solution on this one would be x could equal -1, okay, or x is going to be any number greater than or equal to 3. Okay, so you can write it that way in this case. Showing it on the number line, we can see it there. If you had to do interval notation, I guess we could do something like, I don't know how you do a number by itself, -1 to -1, union 3 to infinity, I guess that would work for an interval, when the first interval is just one number. Or you could probably just write -1 and then union 3 to infinity. All right, so there's some more inequalities for you. All right, and just finally, to wrap this up, just to see this one graphically again, we were looking for which expressions made this, or which values, made this expression greater than or equal to 0. So we can see right at -1, the expression equaled 0. And then once we got to 3, and we went out that way, we can see that the graph or the function, the y values, right, are greater than 0 because we're above the x-axis. So that's why the solution ended up being just the numbers -1, and then everything from 3 to infinity. Okay, so you can always use the graph again just as kind of a confirmation. All right.